I'm Jason Bennett. I worked under Sarah and her grad students, Stephen, Aaron, and Anthony, learning about AdS CFT and how to apply it to strong linear atoms. The outline of my talk is I'm briefly going to introduce the topic. I'm going to say what it's about, why it's useful, and then I'm going to say the work I did with it. Exactly what it is anti-de Sitter space conformal field theory, correspondence. It was discovered in 1997 by Juan Maldacena when he was working on framework and string theory. What exactly it is it relates certain gravitational theories to certain quantum systems. So exactly, it says certain quantum systems go to certain gravitational systems. So when I say certain, I mean a gravitational system in what's called an anti-de Sitter spacetime. If you were to think of a sphere, it would be a shape with a constant positive curvature. AdS can be depicted as a hyperbola, something with a constant negative curvature. And the correspondence says that this relates to something in one less dimension on the boundary of that hyperbola, and it says that a quantum field theory lives there. The special type of quantum field theory is a conformal field theory. What conformal means is that it has a scaling symmetry. It means that if you look at this nice picture by M.C. Escher, if you zoom in or zoom out, things look the same. But this theory is also what's called a holographic principle, where a holographic principle is a generalization of the CFT. So if you look at these coordinates here, we have the normal time and space. But here we have the extra coordinate, which is called the holographic coordinate. It allows us to move in and out of this gravitational system. And we'll talk about it a little bit more when we talk about black holes and lowering temperatures and such. But if we think about this hyperbola in and of itself, it's empty and it has no temperature. So if we were to use the correspondence to equate this to a quantum field theory, it would be a quantum field theory or a conformal field theory at 0 temperature. So if we need some temperature, we need a black hole. And a black hole not only gives us temperature, but it's also like a thermostat. I'll talk later about reducing the horizon and lowering the temperature in the system, and that's how we do it. The horizon is like the radius of a black hole. Here's a really nice picture that Stephen's fiance actually drew. It's a great picture that gives it in a good way. So this was that holographic coordinate that I was talking about. Say, in most cases, we have a black hole in the system, and the two boundaries of our system would be the horizon of that black hole and then the horizon at infinity. But not only is that awesome, but it's also really useful. The correspondence is what's called a weak-strong coupling duality. So it says that on one side of the correspondence, if we have a strongly interacting system, like the quark-gluon plasma that you're going to hear about in a little bit, or ultra-cold atomic gases, or high-temperature superconductors, which I'm going to talk about. It says that if one side of the correspondence is strongly interacting, the other is weakly interacting. Why is that useful? Because the go-to with quantum field theory and quantum in general is perturbation theory. Perturbation theory, just like Taylor series expansion, relies on the ability to expand about something small. So in Taylor series expansion, we had a small angle, like with optics. But in perturbation theory, we have the coupling strength, or the interaction strength of the material. So if the interaction strength is strong, we can do perturbation theory, and AdS CFT gives you the recipe. The system that our group is interested in is superconductors, specifically high-temperature superconductors. Before we go on, superconductivity is the phenomenon where the resistivity of a metal decreases as you go to absolute zero, and as a result of that, current can travel through the material with little dissipation of energy. That's why people will sometimes say superconductivity gives you free energy. The two biggest applications of it are transforming power grids and using them on the chips for circuit boards for quantum computing. So the temperature is the main difference between superconductors and high-temperature superconductors, obviously by the name. From a financial standpoint, all these superconductors that are considered normal, as normal as they can be, are cooled using liquid helium, which is very expensive. But these high-temperature superconductors are cooled with liquid nitrogen, which is considerably less expensive. But other than the financial incentive to do this, there's a whole other slew of physics. Bcs Theory is the name of what normal superconductors were revolutionized with. It won a Nobel Prize. It's very well understood, but this physics is not well understood. So if we want to control these high-temperature superconductors, we need to understand physics and how it works. They have a very rich phase diagram here that I'll explain in a little bit more, but the physics is very different from normal superconductors. So just like the first bubble forming in a pot of boiling water, at each of these boundaries on the phase diagram, we have an instability occurring. So that first bubble at a certain temperature forming makes a phase transition. This is the phase transition that we're particularly interested in isn't just the superconducting phase transition, but also it's called the striped phase transition. So we're looking at a model of striped superconductor. What is the striped superconductor? The striping phase is a manifestation of a broken translational symmetry. So imagine that you're up here at some high temperature. Say this room could be considered a high temperature. Say we have some electron fog with this entire room. I could walk this way or I could walk this way, but it's just fog all around me. I have no idea where I'm going. I don't know that I'm moving. But if we lower the temperature and make this room freezing, we have a striped phase. So if I were to walk in the y direction, I would either be in a column of fog or I would be with two columns of fog on the side of me. But I still don't know that I'm moving. I can either be two walls on me or I can just be in the fog again. But if I walk in this direction, in the x direction, I can take a step and be in the fog. I can take a step and be out of the fog. I've broken translational symmetry. I no longer have no preference in the direction I'm going. So this is what we're going to try to model in our particular superconductor. So we have two things. And not only is this seen experimentally when we cool metal, but this is also something that we can model in our gravitational system. So I talked before about how the black hole is a thermostat. When we want a temperature in our system, here's our temperature axis, we're cooling our metal down, or our gravitational system, we shrink the black hole. A smaller black hole horizon means a lower temperature. So not only are we doing the strength phase, we're doing the superconducting phase. There are two things that cause this to happen. We just went over the broken translational symmetry, and if any of you are familiar with the Higgs mechanism, that is the symmetry that's broken. It's called the U1 symmetry. That's the symmetry that's broken when we get a superconducting phase. Now, in order to see this in our gravitational system, not only do we need a black hole, but we need some fields. We need gauge fields and scalar fields. These two scalar fields, A mu will allow us to have some current density in our system, or charge density, pardon, and B nu will be the phase that we're perturbing to get a striped phase, and chi will be the field that is changed in order to describe the superconducting phase transition. And what we do is we take all of these fields and study their behavior very close to a black hole. So on this y-axis we have temperature. As we lower the temperature of our system, initially, like we have the electron fog up here, we have some current, or charge density, sorry, because we always have charge density. We need charge density before, we need charge density after. But before, we do not have the striped phase, and we do not have a superconducting phase. A normal average state metal isn't superconducting. But as we lower the temperature, or shrink the horizon of a black hole, we see an onset of instability at some critical temperature, just like the first bubble forming in a pot of water. And at that point, not only does the superconducting phase begin, but because in our system, B mu and chi are coupled, they happen simultaneously. So we see the onset of the striped phase and the superconducting phase simultaneously, which is what we want. Apart from this, we're going from 0 to a non-zero value. That non-zero value may not be a million, so all we need to do is kick these fields being chi. So you can imagine if we were in a concave downhill and we kicked the ball, it would go right back to 0. But if we were on a hill and we kicked or a concave downhill and we kicked the ball, it would roll right off. So it's not stable. And if it were not stable, the phase transition would occur, it would grow. So what we do in perturbing these fields is we have a very small quantity, epsilon. We have two fields, two functions, b and omega, which I'll get to in just a second. But since these are coupled, chi as well as b mu, I said b mu is responsible for the behavior of the strict, or the onset of the strict phase. We're going to need two functions that break translational symmetry along the x direction like we wanted in that font. These functions, b and omega, are two functions that we can solve for at the boundaries of our system, the boundaries being the horizon of the black hole and infinity. However, solving these functions numerically is hard because it's a boundary value problem, and a boundary value problem with two boundaries is very computationally intensive. So what we do is rescale this from 0 to 1, so it numerically works. We're not plugging in infinity here. And we have two initial value problems now. And what we do is we extend these functions until they meet at some point, and then we know the whole function. So my work was finding that onset of the instability. I want to know what that critical temperature is that makes this striped superconductor happen. So what I did was I looked at the critical temperature as a function of momentum. Momentum, you'll note, was the other quantity in here. Not only were we breaking it in the x direction, but it needs to be a function of momentum. Because in a normal superconducting phase, the superconducting phase can occur down here, or the onset of the phase, rather. So the thing to note about these graphs is they occur, most of them are bell shaped. So when we see the peak of this bell shape, that is exactly the critical temperature at which, for some finite momentum value, that the instability occurs and begins to grow into the phase transition. I worked with two different parameters. Both the parameters A and C were two parameters that affect how these fields, A mu, B mu, and chi, all interact in the gravitational system. I worked with two. This was done in Mathematica. It doesn't look as nice as this graph because that took about 2 months, and that took about 2 weeks. This was done in C++, and it was much nicer. So in terms of future work, what I've currently accomplished is looking at the onset of these instabilities at some critical temperature in the striped superconductor, not just the regular superconductor. And the next steps are to look at the subsequent behavior of these fields. We now have a black hole in our gravitational system with 3 non-zero fields. We have A mu, B mu, and chi, and we'd like to look at the behavior of all of them. That's what Stephen, Aaron, and Anthony will be doing. Next, from that information, they can garner information about the evolution of the current that's directly related, or they can garner that information directly from the behavior of the A mu, B mu, and chi. And next, the ultimate goal of this was to probe the conductive properties of these metals, specifically what's called the optical conductivity, which is the conductivity as a function of omega. And once they have that, we'll really be onto how these broken translational symmetries manifest themselves in the system. So I'd like to just say what we did so far. We looked at AdS, CFT in a nutshell. Hopefully that entices you as much as it does me. We looked at why it's useful, what systems they can be used on, and what my work did, as well as some future directions. So I'd like to make the following acknowledgments. My professor, my grad students, Professor Swain, and everyone who worked with them that organized the program, Pam and Marina, who helped with paperwork, that was annoying, as well as the NSF for giving us money. So, thank you.
Could you go over again, what did you use C++ and Mathematica for again?
So with Mathematica, what we did was we saw there's a thing in linear algebra called Wronskian. What we did was it looked at the dependence of certain functions. It was very computationally intensive because we have these coupled functions, and we need to find linear dependence of them, and it took just a very long time. They were taking around I don't know how many minutes this is, but around 1,000 seconds for one little point, and these are all hundreds of points. So and this was in C++, which was actually converted to an eigenvalue problem. Okay. So it ran in tens of